Hi, everyone. On behalf of myself and Nancy Bakeman, we'd like to welcome you to the EEBA webinar series. If you're joining us via the live stream today, this is module 4 on window and insulation tables, bringing us up through the IECC 2021. And this is for zones 6, 7, and 8. If you've already taken your window module in 2 or 3, please skip ahead to module 5, which is insulation installation requirements. If you want to see that live, it'll be Thursday, January the 6th again with Joe. So today we've got folks on the live stream. You can ask questions through the Q&A section or in the chat. Joe's going to have a really cool, I really like this program with Slido, Joe. You'll be able to answer some live questions. It's kind of fun. I'm hoping to score 100% today if you're joining us online, you're listening to this on the EEBA Academy on our YouTube page. This is also available in a podcast format through our Better Homes, Better Future podcast. So however you're joining us today, we welcome you. And Joe, as always, it's such an honor to have you here with us. And boy, your insight on the code has been so helpful to so many people.
Great. Well, I'm glad it's been helpful, and I'm thrilled to be here. Thanks again to Aaron and Nancy for having me on and for getting this content out to a wide audience. As Aaron mentioned, this is module 4 today, climate zone 6, 7, and 8 window and insulation tables in the prescriptive path of the code. If you join us in January, when we start up the rest of this series, we'll be talking about insulation installation and then air sealing requirements, followed by a module on mechanical and lighting, and then finally performance path options, including the energy rating index path, the additional efficiency packages in the 2021 code, and how those compliance paths work. So please do catch those. And if you haven't seen the earlier modules, please get them on the recording. If you like what you see today and would like to have me do a live training for you or a more customized training based on what you've done locally with the code, I'm happy to do that. Please reach out and contact me either through EEBA or directly, and we're happy to set that up. Today, during the live webinar, we are going to be doing, as Aaron mentioned, this quiz tool. Don't worry, we're not grading it, but it does help us to know whether I need to go back over something or whether I'm covering something adequately or not. If you have your phone with you, a really easy way to access the quiz is to just use your QR reader, and you can get to it that way. And if you set it up now while I'm talking and introducing the concept, it will be ready to go once you see the quiz pop up during the training. You can also get there via slido.com. You can't click on this slide. It's not live. Obviously, that's just my PowerPoint, and type in the code listed here. And I'll give you a moment to get this set up so that you're ready to go once the quiz is ready. You can also look at the chat, and my understanding is there's a direct link posted in the chat. So if you want to click on something as opposed to typing it in a new window, that should be there in the chat for you, and Aaron's going to repost it in case it was there before you joined or anything like that. So please do get ready with the quiz, and then that way I get some feedback on how well we're doing on some of these concepts, and it's also a way to interact a little bit with the content. So before we start with the insulation tables, insulation and window tables, I want to talk a little bit about what the code is trying to do, because that has some impact on how you comply with the code and what the requirement actually means. So a large part of the energy code, what the large goal in the energy code, is to try to control heat movement, try to keep our hot air in the winter and our cold air in the summer. And it attempts to do that in several ways. One way that heat's going to move, and the energy code has requirements related to that, is conduction. And that's when heat is moving across a surface, a physical surface. So if you think of, maybe standing on a concrete slab without any shoes on, the heat wants to go from more to less, so it conducts from your body through your feet and out into the cold concrete. That's an example of conduction. And the code's window and insulation tables are primarily concerned with stopping conductive heat movement, conduction. Convective heat movement is heat moving through the air, and that's going to be controlled primarily through air sealing, so not through the window and insulation tables, but through other parts of the code. And then finally, radiant heat movement is how the sun heats the earth, and we primarily control that in the code through solar heat gain coefficient in our window requirements, and those are found in the table. So mostly the window and insulation tables focus on conduction, and then a little bit on radiant heat movement through the window solar heat gain coefficient. Here's an example, just a depiction that I think is pretty good, that explains if I'm in a cold climate during the winter or the fall or early spring, and I've got cold air outside and I've got hot air inside, that heat wants to move from more to less. So it wants to go from the inside where we want to keep it to the outside. And the way we prevent that is through insulation, which is going to stop that conductive heat flow. And the code has two different measures for stopping conductive heat flow. One is RValue, and that's the resistivity of a material. So it's resistivity to conductive heat flow. And the more RValue, the higher the RValue, the more resistant that material is, or the amount of material is, to conductive heat flow. So higher is better according to code for RValue. And the code is talking about labeled insulation RValue. It's not talking about effective RValue. So if the code says I need an R20 or better, it's a bat of insulation with R20 or R21. Usually it's going to be R21. There's no real R20 bat, right? Written on the bat or labeled in some way. If it's a blown-in insulation, then there needs to be documentation that a certain RValue per inch is installed. Or spray foam insulation, same thing. A lot of the rigid foams will have it printed there on the foam, the RValue per inch, or again, there would need to be some kind of documentation. So it's the labeled tested RValue according to FTC rules. It doesn't have anything to do with what your framing factor is, whether or not you're creating a thermal break. That's not what the RValue is measuring according to the code requirement. There is an impact on that effective RValue from a building science point of view, but when the code says you need R something, it's an amount of insulation, and the code is going to tell you where you need that insulation as well. UValue is where we start to look at more of the effective ability of that insulation. So the code also talks about UValue in windows, and UValue is the inverse of RValue. It's conductivity. So lower is better. Lower means it's better at stopping heat flow, which means it's less conductive. So windows have a UValue requirement, and lower is better. Also, there's a UValue for a insulation, a building envelope assembly. So if the RValue in the code doesn't work for you, they provide an alternative UValue, and that's for the entire assembly, like the whole wall. And that will include things like stud spacing and framing factor, external sheathing, air films. All of that's included in that UValue calculation for that wall. So that's where you want to look if you're using a material that maybe doesn't fit the RValue requirements. If you find a material that is being advertised as having an effective RValue higher than its labeled RValue, that's not going to work for code compliance. So, sometimes I've seen manufacturers that have a insulating product that also air seals, and they say, well, this has a labeled RValue of 18, but it's an effective RValue of 24 because of the air sealing. That's really nonsense, because the RValue is just a conductive heat measurement. It doesn't have anything to do with the air sealing. Now, that insulation is doing two jobs at once if it's air sealing and stopping conductive heat flow, and that's good. but it doesn't have anything to do with RValue or your compliance with the code. So keep that in mind when you're picking out your insulating materials. For the tables we're going to talk about today, we're entirely in the prescriptive part of the code. So it's kind of like a checklist. Do all these things and you comply. Within the prescriptive path, though, there are several options for compliance. I talked about insulation RValue, assembly UValue, so that's the whole wall or the whole attic, or a whole building UA, and that would be, that's an area weighted average of the UValue. So it's taking the area weighted UValue of your walls, ceilings, floors, basement walls, windows, and it's creating an ability to trade off as long as the whole building meets that area weighted UValue. And I'll talk more about that in detail in a little bit. By the way, please feel free to stop me as we go if you have questions, or write into the chat, excuse me, and Aaron will ask me questions as we go. So starting off with windows and what's in the prescriptive tables, Climate Zone 6, the purple highlights here are how the code is, where the code has gotten more stringent through the years. So we see in 2012 change in stringency where we went from a 0.35 to a 0.32 window. 0.32 window is pretty common window now, not too aggressive as far as rigor of the code. We also saw a 0.55 skylight UValue for the first time. So the first column on windows is vertical fenestration. The second one is skylights. And then in 2018, we saw the code move again to a 0.30, and that's where it's remained for 2021 in Climate Zone 6. So no big jump in 2021 on windows. 0.30 again is a fairly achievable window. There's definitely a lot of product out there at that level. Solar heat gain coefficient is not required in Climate Zone 6. So solar heat gain coefficient, again, is a measure of how well that window will stop radiant heat movement across the window. Because Climate Zone 6, 7, and 8 are colder, they don't have a solar heat gain coefficient maximum like some of the other climate zones have, because the thinking there is it's a heating driven climate, and added solar heat will over the year in general actually lower energy costs and energy use by taking advantage of some of that free energy from the sun. As we get further south, that's going to overheat the building where it's more cooling or mixed in its nature, and in that case there is a maximum cap on the solar heat gain coefficient measurement. There's also an air leakage requirement for windows. It's not in the prescriptive tables, but I list it here because it is a window metric. This is tested in the factory, so it's not. This is not your blower door target. This is your target for the window itself, and the manufacturer should be testing this. It's not always tested, so it's important to make sure that's on the label in your window because the test itself isn't mandatory, but any code in an IECC International Energy Conservation Code jurisdiction should have this test done because it's been a requirement for quite some time, since 2009. So make sure that the home does have that air leakage number on there. Climate Zone 7 and 8, this isn't a lot of the country. It's very high altitude areas, some parts of the northern, small part of the north in the country, and then a lot in Alaska. But you see here very similar numbers to Climate Zone 6. Again, we moved to a 0.32 U factor. Again, lower is better for U factor in 2012, and then a 0.30 in 2018, and no change in 2021. So these climate zones aren't seeing real big jump in stringency from what they had in 2018 for windows. It is important when you're determining your window compliance that your windows all are labeled with the NFRC sticker. That's a mandatory requirement in code. It has to happen, or you end up having to accept default U factors. So if you have a vinyl double pane argon filled window, it probably performs pretty well, and the code is going to make you accept a default U factor of a 0.55, which is not a very good window as far as conductivity. And that's not going to comply with code. As you can see here, you need a 0.30 or lower. So you have a non-compliant window if you don't have that sticker, and you're going to end up having to use either the performance path where you're adding efficiency somewhere else to make up for the fact that that window is not compliant, or if this is only one window, maybe you can trade it off with some of the other ones. And I'll talk a little bit about how you would do that in a moment. But it's important to have that sticker so that you can avoid this problem. There are a number of options if you do have some issues with your windows not quite being compliant with the code requirements. 0.30 U factor is the main one in these climate zones. We talked about the whole building UA, so that's where you're trading off U factor or U value across the whole building envelope. So maybe you have a super insulated home and your windows aren't quite meeting that U factor, U value. You may comply using that, and I'll talk about that again a little bit more later. You can also do an area weighted U value calculation just of your windows. So for example, if I've got one window that's missing the sticker, but the rest of my windows are actually better than code, I can do an area weighted average of all my windows and show compliance by showing that on average, my windows are compliant. The same thing goes with solar heat gain coefficient, although that's not actually applicable in climate zone 6 to 8. There's also a window and door exemption of up to 15 square feet of window area and 24 square feet of door area. So if you have a situation where maybe you have an antique window that was taken from another home and installed because you really like the look of it in a new home, or maybe you've got, again, that situation where one window is not compliant, you can actually exempt up to 15 square feet of window from your compliance. So that's important to keep in mind if you do have, again, that kind of odd one-off issue with a window not being compliant.
And Joe, that's 15 total square feet of windows, right?
That's right. 15 total square feet of windows, 15 total square feet of doors as well that can be exempted. And that's, again, not a lot, 3x5 window and you're there. So that's something to keep in mind. And you know, obviously we want more efficient windows. The better the U factor, the better your home is going to perform and the less cold spots you're going to have. But if you do have an issue, there is some compliance flexibility there built into the code.
Great.
So we're going to have our first quiz now, and I'll give you a moment if you haven't already gotten into the quiz system. You've got the QR code here on the screen. If you've got a phone, you can go to slido.com with this code if in another window, or you can click on the link that should be in the chat and use that there and hopefully access the window or the question. So our first question is, in climate zone 6 to 8, a maximum U value of 0.30 is required to try to control what type of heat movement. So the U value is trying to, or lower U value is trying to control what type of heat movement?
I did put the one-click way to get to the quiz in the chat function as well, if you'd like to just click on that and join the quiz.
So I'll give folks just a little bit longer to participate. And this one's I'd say a fairly easy one, but they do help me to know whether the concepts are getting across. I'll give you just a minute longer and then I'll go forward. Okay. So our answers that we have here are correct. Conductive heat movement is what the U value is trying to control. So lower U value, the less conductivity that window has. In climate zone 6, next question, climate zone 6, if I install a window with a U of 0.32 instead of the required 0.30, that window could still comply using which compliance option. There's actually multiple options you can pick here. So you can choose any option or more than one that you think would be compliant. But just a moment longer here. Okay, so yes, the whole building UA trade-off could be an option if you've got something where you're better than code somewhere else. Area weighted window U value calculation, if some of your windows are better than code, you might be able to use that, or that 15 square foot exemption. All of those are correct. RValue method is the only thing that doesn't apply. There's no RValue listed for windows in the code. Okay, again, feel free to stop me and ask questions if you've got them as we go. The next section is on insulation R values and U values and how those tables in the code will work. So the first table here I've got on Climate Zone 6 shows how the code has changed throughout the years. We saw some change in stringency in this climate zone in 2012. And then in 2021, the big changes in attic insulation or ceiling insulation. So let's talk about ceiling R value for a moment. That column there is just going to give you an amount of insulation. So R60 or R49, so that's labeled bats or inches of blown in insulation, and it's calculated by its tested R value per inch. The R60 is obviously a big jump over R49. It's one of the major increases in stringency, the only one in Climate Zone 6 for the building envelope. So keep that in mind. That's going to be the big jump for a lot of builders who are building in this climate zone that might not be used to this kind of construction. And I'll talk a little bit about what your flexibility around that R60 attic is in a little bit. If we look at the next column, wood framed wall R value, these values work a little bit differently. The ceiling R value just has one value there, but there are several options in the code in wood frame walls. So if we look at the 2021 row there, we have 20 plus 5, 13 plus 10, or 0 plus 20. And I'll explain what those mean. 20 plus 5 means R20 cavity insulation plus R5 continuous insulation. Same thing with the next option, that would be an R13 cavity insulation plus R10 continuous insulation. And then finally, there's an option for no cavity insulation, and that's 0 plus 20. And that's a 0 in the wall, and then an R20 cavity insulation. Interestingly, the climate zones.
It's an R20 continuous, right,
That's
Joe?
right, R20 continuous, excuse me. What I find interesting about this is in climate zone 4 and 5, for example, they have the same first two options, R20 plus 5 and 13 plus 10 in the wall R values, but then they have a 0 plus 15 instead of a 0 plus 20. So I'm not exactly sure just why that one option is different in Climate Zone 6. Well, it happened because that's what passed in the code, but there is a little bit of an inconsistency climate zone to climate zone as far as what the equivalencies are here. So if you have an assembly that meets these requirements, you can just build it, meets or exceeds. So if I'm putting R21 in my wall, an R21 bat, and an inch of XPS foam on the outside of my building, I would have R20 plus 5. R13 plus 10 might be a better option in some areas where moisture might be a concern and you have a better hydrothermal model with more insulation to the exterior, and that might be 2 inches of XPS foam and 2x4 wall instead of the R20 plus 5. And then 0 plus 20, that's obviously all continuous to the outside. For anybody who's not doing one of these assemblies or better, you might have to go to the U factor table, U value table to use that. For example, I can't do R21 plus 4, even though I'm buying an R21 back because that's what they sell, because that plus 5, that's specifically located to the exterior. It's not additive. I don't just need a total of R25, right? In fact, I don't just need a total of R23 in the next option. I need a 20 in the cavity plus a 5 to the exterior. And if I go less than 5 to the exterior, it's not a one-to-one trade-off there. So you're going to have to use the U value and calculate exactly what your U value is going to be in order to comply, rather than just an R value compliance. For mass walls, the next column, that's things like concrete block, poured concrete, timber. There's a lot of different things in the code that are listed as examples. ICF, insulated concrete form construction. That's a 15 or 20 in Climate Zone 6. And what that means, 15/20, it's a little different than wood frame walls. The 15 means if I've got 50% or more of my insulation to the exterior of that mass wall. And if I've got more than 50% to the interior, I have to put in R20. So that's what that slash means in this column only. So as we get to the other columns, it's going to be a little different. It's important to look at the footnotes if you can't remember what those breakdowns mean in the table. A really great way to do that for a mass wall is an ICF wall, because it's got 2 rigid foam layers, usually around R10 or 11, and you're going to be able to meet either the 15 or the 20 as a total R value with that assembly. Floor R value is R30, and that's floors over unconditioned space. So a floor over a garage, or if you're not conditioning the basement, floor over the basement, something like that. For basement walls, this works differently than the mass wall. Mass wall is an above grade wall. Basement walls might be made of the same thing, but they're treated differently. So for a basement wall, the 15/19 means 15 for continuous insulation and 19 for cavity insulation. So cavity might be if I'm finishing the basement and I've got a framed wall, I've got insulation in my cavities. The 15 could be continuous, is just, could be a blanket, it could be rigid foam, anything like that in the basement. And then in 2021, there was actually an additional option added here, which is 13 plus 5. So that's a combination of continuous and cavity. Again, R13 cavity insulation plus 5 continuous insulation. For slab R value, this is just slab on grade. So Climate Zone 6 to 8, more basement dominated, right? So if you have a slab on grade, that's where this comes into play. It's not that it's a bad idea to insulate your basement slab. It's just not regulated by the code. So slab on grade, you need an R10 for 4 linear feet. And that can be interior or exterior, as long as the slab insulation is coming to the top of the slab edge, and then it's extending 4 feet. But it's an R10. And then crawl spaces, this is conditioned crawl spaces. You insulate the wall instead of the floor above. That has the same requirements as the basement, the 15 continuous or 19 cavity, and then the R13 plus 5, which is 13 cavity and 5 R5 continuous. Does anybody know why it's kind of weird that they have R19 cavity insulation? I know you can't respond to me, but I'm going to tell you. It's weird because R19 isn't made for a 2x6 cavity. It's
Right.
It's like 6.25 to 6.75 inches. So it has to be compressed to get into the cavity. It's really an attic insulation. And so it's a little bit odd to me that that's what's in the code for basement or crawl space cavity walls, because you're still going to be using the same dimension lumber there, which is actually 5.5 inches if you've got a 2x6. So that's a little odd to me, but that's what the code says. So R19 would be the cavity insulation requirement there. Here are the U values that correspond with those R values, or they're meant to correspond. Again, as I showed here, the 0 plus 20 is different than the 0 plus 15 in another climate zone. So they're not always exactly equivalent, all the different options with this one U value. But this is the U value that's required if you're doing U value compliance in the code. And it's also what you'll use as a reference for a UA calculation. So you'll see here, we went from a 0.026 to a 0.024 in attics or ceiling insulation. And that corresponds with that change from a 49 to an R60. It's not a big jump in U factor or a big drop in U factor for that R60 compared to the R49. You're not getting a ton of extra U value. And part of that is the compression at the eaves that will happen with an R60 bat. So that's something to keep in mind there. So if you're using U value compliance, maybe you're using a SIP wall, structural insulated panel, and that's totally continuous insulation. You've got a different U value than the R value listed in the code. Maybe you're using it for your roofs. You're going to want to use that U value compliance to meet the code instead of the R value, possibly. It's just something to keep in mind if your way of building doesn't exactly meet those prescriptive tables. Maybe you're using advanced framing and you have less wood in your walls, so you have more insulation, and you want to take credit for that in your compliance with the U value. This table is an option for you. Moving on to climate zone 7 and 8, this should look very familiar because it's very familiar, very similar to the climate zone 6 values. Again, the major change in stringency there is the R49 to R60 in the attic for climate zone 7 to 8. Everything else, not everything else is exactly the same, but the cells work the same. You'll notice the mass wall is higher, 19 for if more is to the exterior and 21 if more is to the interior. Still, an ICF wall will meet that. That's kind of the high end of mass wall construction, but you could use just a mass wall, block wall with layers of concrete, with layers of rigid foam or something like that to comply. Floor R value is a little bit higher than climate zone 6. It's an R38, again, for floors over unconditioned space. And then basement, slab, and crawl space are all the same as climate zone 6. But the only thing that's really changed is the R60 in ceilings, and then these couple of additional options here, the 13+5 in basements and crawl spaces, and conditioned crawl spaces. That's a new addition to the code there. Again, just to look at the U value, you'll notice, for example, in the mass wall, I've got a 0.057 U factor, and it's a 0.060 for climate zone 6 because I've got more insulation in this case. Mass walls, it is important to note that that U value in the table, the 0.057, is really linked to the R19 in this case. So if more is to the exterior, it's giving credit for a U value of 0.057. If more is to the interior, then there's a different U value that's required in climate zone 6. Climate zone 7, it doesn't move. Again, this is kind of an illustration of how the U factor and what's required in the R value isn't always in sync. But if you're in climate zone 6 and you're using U value compliance as opposed to R value, you have a more aggressive 0.057 instead of 0.060 U factor. One way that you have some flexibility in the code, so I talked about the R value and U value tables, and that's kind of telling you what you have to put in. But the code does allow some flexibility even beyond having those two options. And one of those main ways that the code provides flexibility is for attic insulation. So I'm sure a lot of you have used this already, but there's a type of truss called a raised heel truss, which has higher height at the heels. And what that does is it allows us to install attic insulation that's not compressed at the heel. Because as you compress insulation like fiberglass, cellulose, things we typically put in attics, it's going to lose R value. So the goal of this this allowance in the code is to provide a way to not compress the insulation at the eaves using a standard truss and instead use a raised heel truss. And the code says that you have to install the same level of insulation all the way across the ceiling, including over the top plate, extending all the way over the top plate at the eaves in order to take advantage of this requirement. Now, here I'm showing R49 to R38. That would be what you would do if you have a 2018 code or earlier. You could go from an R48 to an R49 to an R38. So what that means is I've got R38 all the way across the attic, including extended over the top plate, uncompressed. In the new code 2021, because I've got an R60 target, I can only go down to an R49 now. And I've got to have a different raised heel truss than I would have had for that R49 to have enough space. So it may be that if you're already doing raised heel trusses, you've got to order a new raised heel truss as opposed to what you were ordering in the past to fit that R49 uncompressed instead of R38 uncompressed. But that's some flexibility that's allowed in the code because we're really getting a better performing attic out of that where it's not compressed there at the eaves.
Good. Joe, quick question came up. Where can we find these insulation tables in the IECC? What section would it be?
Sure.
And I assume it would be the same section in the 2018 versus the 2021.
The numbers are actually slightly different, Aaron,
Okay.
believe it or not. So 402 is the general section, and that's still the general section you need to look at. The only switch that happened in 2021 was that, as you can see here on my screen, the U value table comes first for whatever reason, and the R value table follows that in 2018, and before it was reversed. Mm-hmm. But so section 402 is where you'll find envelope requirements. This is also where in module 5 in January, if you join me for that, this is where most of the requirements are that have to do with insulation installation requirements. But that's where you want to look. In 2021, it's 402.1.2 for U factor and 402.1.3 for R value. That's switched in the 2018 and earlier code.
Great, thank you.
You can see it there. Great question. One other way that the code allows some flexibility for attic ceiling or ceiling insulation is ceilings without attic spaces. So a cathedral or vaulted ceiling, you can go to a R30 for part of that assembly. So the code says I have to have at least R30, and I can only do this in 500 square feet or 20% of the insulated roof area, whichever's less. So can't do my entire attic this way, or I can, but I have to do a UA trade-off or a performance path or something like that. Prescriptive R value compliance only gives me a little bit of flexibility for some areas on the roof. So if you've got portions that are without attic, as shown here kind of in this diagram, you could do R30 in that space. You could also do it, say, in an addition where maybe the slope of the roof on a add-on space is not quite high enough to accommodate R60. It's possible that that space is less than 20% or 500 square foot of the total roof area, and then you could do that. Now I'm going to go through an example of a UA trade-off. I've talked about this a lot. Again, keep those questions coming if you've got them, and we'll fit them in as we go. So for demonstrating compliance using the UA calculation, most people are going to use some sort of software. So DOE has a free software called ResCheck. You can access it online. It's fairly easy to use. And you don't have to have any credentials to get it. You can also get a UA calculation done by softwares that might do your HERS rating if you do above code programs, or an energy rating index if you're using that compliance path. Those softwares generally also do a UA calculation, and I know that they are being updated to include 2021. I know that the ResCheck already does have the 2021 UA calculation. This is not a whole building performance calculation or a performance model. This is just a calculation of a area weighted U value for your building envelope. Even though a software is most often going to do it for you, I do want to show you how it works, because I have gotten a lot of questions on code hotlines that I've operated where people will say, I don't know how to calculate my UA. I can't figure out the software. How do I know if I'm compliant? And this is generally how it works. So I've got an example here for Climate Zone 6. And what we're going to do is we're going to compare the required U value, and we're going to multiply that times our area for each assembly to get our allowed UA or UA allowance for the building. And we're going to compare that to what we're proposing in the house that we're building. So the required U value is going to come from that U value table that I showed you in the code. Window U value is 0.30 or lower in the code. So if I've got 180 square feet of window, I have a UA allowance of 54 from my windows. Now, I don't have to keep that in windows. I can move that around the building envelope, but that's what I get from the amount of windows I've got. And this square foot area should match in both calculations, the compared home required UA and the proposed UA. So for above grade walls, for that 20+5 or whatever it is of those options, I've got a 0.045 and 2,600 square feet of wall area, above grade wall area, and I have a UA allowance of 117. For basement walls, I have a UA of 0.050 and 1,020 square feet of wall area there, assuming an 8-foot basement, and that's a 51 UA allowance. And then the ceiling, that R60 is a 0.024 U factor, and 1,000 square feet of attic space gives me a UA allowance of 24. And I add all those up to get a total UA of 246. Now I can do whatever I want over in these other values, as long as my total UA for the proposed amount is equal to or less than the UA for the required amount. So let's say I increase my window performance from a 0.30 to a 0.27. This isn't a really aggressive window. It's still a double pane window. I know a lot of builders building in these climate zones are looking at triple pane now, and that's a great way to go if you can make that work. But here I've got just a very good double pane window, meet Energy Star requirements currently for windows. So a little bit better than code on my window. And now I have a 48.6 for my proposed UA on the window. So I'm doing a little bit better there. But because I don't have comparatively a lot of square footage, that has a small impact compared to, say, really beefing up my walls or something like that, which would have a bigger impact on my UA flexibility. Above grade walls, I'm going to stay with the recommended amount of R20+5, and I've got a 0.045 U factor, 117 again is my proposed UA. Same thing with the basements. I'm going to put in the code required amount and end up with a proposed UA. But what I want to do, because I'm not used to building that way, is still put in my R49 in the attic, and I'm using a standard truss. So I'm not using the raised seal truss, I'm using a standard truss. And I get a 0.026 U factor for that R49 in a standard truss. And that means my proposed UA is 26. If I add that all up, I've got a 242.6, which is still just under where I need to be. So I'm compliant. So you can see here in this very simple example of a UA calculation, what I needed to do was change my windows and get a slightly better window, still a very available window. And I was able to change from an R60, which I wasn't used to in the attic, to an R49, which I am used to because that's been code for a while. So not advocating you trade off your attic insulation with your windows. That's an example of what you can do using the UA compliance path. And it's a way that you can get a similarly robust envelope from what the code would require, but pick the option that works for you best from a financial standpoint, from what your trades are used to putting into, whatever it is, you can have a little flexibility there within the prescriptive path. So now we're going to go on to our questions here, our quiz questions. So please participate if you're with us live. The goal of the RValue requirements in the energy code, RValue requirements for insulation in the energy code, is to stop what type of heat movement? I'll give you a moment longer to answer here. RValue, I'll give you a hint, is resistivity. Okay. And so that is confusing because radiant does start with R, but RValue is not radiant heat movement, it's conductive heat movement. Somebody just changed their answer there. So that's important to note because there are products out there that advertise themselves as a radiant insulator. And radiant barriers really don't have an R value. There is a way to use a radiant barrier in combination with a airspace, not how they're typically installed, in order to change how the heat flows across that building envelope. But a radiant barrier by itself isn't going to stop conductive heat movement. In fact, it will conduct directly across that substance. So that's what the R value requirement is intending to do. And it's important to remember that that R value has to be tested according to FTC rules. A basement wall insulation requirement of 15/19 means which of these options? I'll give you just a moment longer to pick the correct answer. Okay, everybody got this one right. That's great. R15 continuous insulation or R19 cavity insulation. That's what the basement wall requirement means in that table. Next question, true or false, a manufacturer can claim additional R value for an insulating product that also air seals. True or false? Give this one just a moment more. It should be pretty simple. Okay, everybody got that right. False is the correct answer. Air sealing does not add R value. It does improve the efficiency of the home, but it doesn't add R value. True or false, an above grade wall, if the code, in an above grade wall, excuse me, if the code requires R20+5, I can install R20 cavity insulation plus R4 continuous insulation and still comply using the prescriptive R values in the table. And everyone got that one correct as well. That's right. Those numbers, R20+5, are not additive. It doesn't mean R25 total. It means R20 cavity plus R5 continuous. And I especially can't take away from the continuous side and add to the cavity side in a one-to-one way and have that be equivalent. You could go the other direction, really, and you would be better than code, but you'd still have to do the U value calculation because the code's having specific amounts here in specific places. Okay, that's the end of our quiz. Everybody did great. Now I'm going to end up with the last few slides here are just different examples of what innovative builders around the country are doing for their insulation. We have a few minutes left here, so please do type in your questions into the chat if you've got any, and we'll try to answer them while you're here with us live. This is an example of a spray foam insulation. This is in a Western climate, so it's in a dry climate. I believe this is open cell spray foam in this case in the wall here. This is an example of a spray foam, but it's only part of a assembly. This is the first step in a flash and bat construction. So they've sprayed an initial thin layer of spray foam, and then they're going to add onto that a bat insulation. And that's a way to use the properties of spray foam while minimizing the added cost and still insulating the rest of the cavity with that insulation. This is a rigid foam insulation applied to the exterior. It's taped at all the joints and seams as it should be in the code. And typically this is going to be combined with some cavity insulation. So that might be, looks like maybe an R5 if it's an inch of that foam, that particular foam, which means they would need an R20 in the cavity or better to comply in any of the climate zones we're talking about today. Same thing here. This is a exterior insulating product. It's actually a structural sheathing product that has an insulation with it. I'm not sure if this is the R5 product or whether it's something lower than that, in which case you would need even more cavity insulation or to do some kind of UA trade-off to get this wall to comply in combination with cavity insulation. If it is R5 in this product, then you would only need the R20 in the cavity. This is an example of a double wall construction. See a lot more of these in the climate zones you're working in. If you're in a humid climate zone, it's important to do some moisture modeling here to make sure you know where your dew point is in this wall. But the way the double wall works is here we've got two 2x4 walls with a gap in between. And the 2x4, the insulation is typically blown in this assembly, so it fills the entire space, and it creates a barrier or a layer of continuous insulation between the two cavity walls. Here's another example of a double wall, and I've seen walls getting R40, R60 in some of these double walls, so they can get very well insulated using this construction. You'll notice in this picture the deeper window jambs that are necessary, so there is some adjustment in how you're building these walls. But it is an option. This is a structural insulated panel. And what that is it's a rigid foam between two structural panels. It could be plywood, OSB, magnesium oxide, I think is one of them. There's a lot of different things that the structural panels are made out of. And then the foams are EPS, XPS, polyiso. It could be different foam materials that are in between those two panels.
That particular version shown, that looks like it's a neoport type product. Is that right?
That's what my eye would say as well. I think that you kind of can tell by the color of the foam sometimes. Yeah. So I'm not exactly sure. I didn't get this from the manufacturer. This is just a builder's picture, but if I had to guess, yeah, that might be what it is.
Yeah, I think there's a little more R value per inch in that particular product.
Do you know what the R value per inch is offhand?
I will Google it while you're talking.
Yeah. So in that case, you can comply with any of the 0 plus 13 or 0 plus 20 or whatever the continuous only insulation is, or you can use the U value to demonstrate, because it's not interrupted by framing, that this is meeting the U value in the code. It's another example of a SIP there. It's I think that might be the spline at the roof, but I'm not totally positive about that. This is a blown-in insulation, not incredibly innovative in that it's been around for a while, right? But the nice thing about blown-in insulation is it conforms readily to the cavity, which is going to help us in a lot of the installation requirements later, because it goes around those plumbing and wiring and other obstructions in the cavity and kind of fills the space.
Joe, it looks like an R value of 5 per inch.
Right. Okay. So if we look at that, I'm just eyeballing it, that's probably what, 4 to 6 inches, somewhere in there, which means we've got an R20 or 30 in that assembly.
Sure.
This is an ICF insulated concrete form, and this is built in blocks, and it's again 2 layers of rigid foam, and the concrete is poured in between them as it's done on site. It's incredibly strong and and easy to air seal, really, really tight. This is another picture of those ICFs. Again, it's done kind of piece by piece and put together there on site. This is another spray foam. I think this is closed cell spray foam in Minnesota. So this is in a climate zone 6, I believe. And here they've sprayed the wall and the attic. So it's an unvented attic space. And that's all of the examples I have for you today. We do have a few minutes left if anybody's typed in any questions.
Yeah, I don't have any questions right now. We can wait a second for some to come up, but if you've just completed this module, you can now go to module 5 on installation requirements. Of course, it won't happen until Thursday, January 6th, and we hope that you can join us there live as well.
That's right. And I'm looking forward to it. And please do contact me if you need any other code training sessions, or if you just have questions about what you've seen here today.
No, Joe, we really appreciate that offer. We had a builder, well, it was probably beginning of the week, right, that was working on a zero energy home, and you were able to kind of point out some things with the window U factors required and where things were at. And you've always been a huge help to the community. So we appreciate that.
Great. Thank you so much,
Great.
Eric.
Thanks, Joe. We'll see you next year. Happy holidays.
Same to you.
All right. Bye now.
Thanks, Joe.
Thanks.